Okay, so hopefully now the audio should come through. Let me see. So Amit hasn't joined yet, right? Not yet.
He will be there in 2 minutes.
Sure.
Yeah.
Yeah, there's a little bit of a lag between uh, the actual event and it streaming on YouTube.
Okay.
So yeah, just give me a now the audio should come through.
Yeah.
Let me see. So Amit, yep, it's fine. So we can go back. We'll go live now. All right, so hello everyone. Welcome to the next talk in the Theory Matters series. The speaker today is, we're very pleased to have Eric Zhang, who is a postdoc at the National University of Singapore. He's currently working with Professor Vincent Tan, and he's working on various topics in information theory. He received his Bachelor of Engineering with first class honors and PhD from the Department of Information Engineering at the Chinese University of Hong Kong. There he worked with Professor Siddharth Jaggi and Professor Mayank Bakshi. He has a wide variety of interests and has very interesting work on we started off with covert communication, but more generally he is interested in information theory and statistical machine learning. Today he'll be speaking about some of his recent results on community detection, and we're eager to listen about this. So a quick note to all our audience: if you have any questions, please feel free to type them up in the chat box. We'll be monitoring that. But even otherwise, you may just unmute yourself and ask. So Eric, hopefully that's okay if we interrupt you in between for questions.
Yeah, sure.
Okay, thanks a lot. Yeah, so also for people who are watching it on YouTube, we'll try to monitor the comment section over there or the chat box for questions, but there may be a little bit of a lag. But yeah, over to you, Eric.
Okay, thanks for your introduction, Zhang. Yeah, my name is Qiaosheng Zhang. You can just call me Eric. I'm a postdoc at National University of Singapore, working with Professor Vincent Tan. And today I'm very happy to share our recent work on community detection with you. So in the first part of the talk, I will review some classical community detection problem, which is community detection on graphs. And in particular, we are interested in this random graph model called Stochastic Block Model, SBM. And I will review some classical information theoretical results for SBM. And in the second part of the talk, I will introduce our recent work, community detection on hypergraph. And in particular, we are interested in the so-called Hypergraph Stochastic Block Model, HSBM. And I will introduce our information theoretical result for this HSBM, and also present our efficient algorithm as well as a converse result. So the first part is the classical problem, community detection on graph. So first, let me use this example to motivate in the study of community detection. So around 2004, during the US election, some researchers has collected some data from the internet to construct a so-called political block network. And in this network, each node represents a political block, and each edge represents a reference between two blocks. So as we know that in the US politics, each political block may be either liberal leaning or conservative leaning. So our objective is to, based on this graph, we want to distinguish the two communities. One is liberal leaning blocks, and the other is conservative leaning blocks. And we want to do so by without reading the content of each block. We just want to do the community detection based on this graph. So this is basically what community detection aims for. So there is a very popular random graph model that is widely used for studying the community detection problem, which is the stochastic block model, SBM. So it is a random graph model. And yeah, first, let me introduce this SBM by introducing a very simple variant called binary symmetric SBM. So in this model, we have n nodes, which are partitioned into two communities of equal size. That is, for each communities, it contains exactly n over 2 nodes. If two nodes belongs to the same communities, then they are connected with probability alpha. And if two nodes belongs to different communities, then they are connected with probability beta. So this is how we generate a random graph under the binary symmetric SBM. So next I will introduce the general SBM, which is a more general version of the SBM. So in general SBM, we have more than two communities. So we assume that n nodes are partitioned into k communities of relative size p. Where p is a length k vector, comprise p1, p2, all the way to pk. And we can assume that there are n random variables, x1, x2, all the way to xn, which correspond to the n nodes. And each xi just represent xi just represent which communities that the ith node belongs to. And in the general SBM, we assume that each xi is distributed according to this length k vector p. So you can regard this p as a relative size of each communities. You can also regard this p as a probability distributions. So each xi is distributed according to p. And also, if for two nodes, they are connected with probability Qij if they belong to community Ci and the community Cj respectively. So for example, these two nodes both belongs to community C1, so they are connected with probability Q11. And similarly for this edge probability is Q22, and this edge probability is Q33. So we also have some cross community edges. For example, this this edge connects one node in C1, one node in C3. So the edge probability is Q13. So basically, this is how we generate the random graph under the general SBM. So we note that this general SBM is fully characterized by the length k vector p and also the set of value Qij. So this is just the description of the general SBM. So once we generate a graph, then we want to, the estimator wants to partition the communities. So they use a estimator phi to output estimate length n estimate x hat comprising x hat 1 all the way to x hat n. And we hope that we can partition the nodes into different communities. And the goal is just to recover the partition. And we note that it is not necessary to require that x equals to x hat exactly, because we can consider this example. So for this is a ground truth x1 all the way to xn. So the ground truth satisfies that the first half of the nodes belong to community 1, and the second half of the nodes belongs to community 2. And if the estimator can output such a estimate x hat, which satisfies that the first half of the nodes belong to community 2 and the second half of the nodes belongs to community 1, then we are also happy because this estimate also partitions the n nodes into two different communities correctly. So next I will introduce the measurement which measures the accuracy of the output x hat. So we define the misclassification proportion, this L between x and x hat as the following expressions. So roughly speaking, we want to minimize overall permutation pi from the set of permutations from k to k, and this part is nothing but the fraction of misclassified nodes under this permutation pi. So what we can do a sanity check that if we have this ground truth and this output estimate, then this definition of misclassification proportion L returns 0. So which means that okay, we recover the partitions of the of these nodes, although we do not guarantee that x equals to x hat.
Hi, Eric.
Hi.
This is Zhang here. Oh, so there's a question by Vinay. So will you be interested in the case when Qij is dependent on P, or are they completely?
Completely independent.
Okay.
Yeah. Okay, thank you. Okay, let's get started. Let's continue. So so now I will introduce several recovery requirements. So the first one is the so-called exact recovery, which means that we want to recover all the nodes correctly. Using the math, this exact recovery just requires that with probability approaching 1, this misclassification proportion L between the ground truth and the output estimates x hat equals to 0 exactly. So that is, we want to correctly recover all the nodes. And the second requirement is the almost exact recovery, which requires that with probability approaching 1, this misclassification proportion between the ground truth and the estimate equals to label 1, which means this quantity tends to 0 as it tends to infinity. And the third requirement is the so-called weak recovery. So it is a little bit harder to define, give the definitions. But we just see briefly that weak recovery is just requiring that the estimator can do better than just random guessing. So in this talk, I will mainly focus on the exact recovery. So we hope that all the our requirement is that all the nodes should be estimated correctly. So we recover the partition correctly. So next, I will introduce some classical result, which is the fundamental limits of exact recovery in the stochastic block model. So first, let's look at the simplest case.
This is Amit. Sorry to interrupt. I just wanted to understand one part about the problem. So, what does the estimator depend on? I know the number of nodes. I know the P and the Q vectors.
Yes. Thanks. That is a good question. So
it depends on the graph.
Yeah. So the estimator, the input of the estimator is just a graph, and at the beginning you can assume that the estimator also knows the number of communities, and you assume that the estimator knows. Sorry, I can go back. You can assume that the estimator knows this p vector and also this this Qij, this set of values, and also knows the graph. And but actually later you can show that even if the estimator do not know the number of communities and the p vector, it is still possible to recover the partition of the communities. Okay.
Thank you. Thanks.
Let's continue. So we are interested in exact recovery, and we are now introduce the fundamental limits of exact recovery under the binary symmetric HSBM. So recall that in this regime, in this model, two nodes are connected with probability alpha if they belong to the same community, and with probability beta otherwise. So this fundamental limits has been solved by these two works in parallel, and in particular, they are focusing on this log degree regime, where alpha and beta scale as order log n over n, and in particular, we define the pre-constant as a and b here. So why we are interested in this log degree regime, because it turns out that the threshold for exact recovery just occurs in this log degree regime. If we consider a more sparse regime, for example, if alpha and beta scale as order 1 over n, so one can show that with high probability, the graph is not connected. That is, there exists some isolated node which are not connected to any other node. So in this case, once there exists isolated node, then you cannot do the exact recovery because you don't know which community that the isolated node belongs to. So then there's no hope for exact recovery. So this partially justified why we are interested in this log degree regime. And so for intuitively, if this alpha and beta, the difference is larger, then it is easier to partition the two communities. And if the difference between alpha and beta is smaller, then it's harder to partition the two communities. So this work shows that there is a sharp threshold, which is that they show that if the absolute value of square root of a minus square root of b is less than square root of 2, then exact recovery is impossible. And if, on the other hand, if this quantity is greater or equals to square root of 2, then exact recovery is achievable. And also, they propose efficient algorithms such as semi-definite programming-based algorithm, and another one is a spectral method based on plus some local refinement steps. So this is the fundamental limits of exact recovery under the binary symmetric SBM. So although this result looks very simple, but actually they are very beautiful, and it's non-trivial to derive. And these two papers got the 2020 Information Theory Society Paper Award. So next, I will go to the more general SBM. So recall that for the more general SBM, the K communities are of relative size P1, P2, all the way to Pk. And two nodes are connected with probability Qij if they belong to community Ci and Cj respectively. So for the fundamental limits, so it has been solved by Abbe and Sandon. Again, the regime of interest is a log degree regime, where this Qij is scaled as order log n over n, and we define the pre-constant as this capital Qij. And in order to present the result, they define the so-called Chernoff-Hellinger divergence between two communities Ci and Cj, which is written as D plus Ij. And it takes a form that we have a maximization over auxiliary variable t, and this part is just some function of this p vector and also this Qij, the value of Qij. So speaking, this D plus Ij, the Ch divergence between community I and community G, just measures the discrepancy between the two communities. So for example, if we know P1, P2, and P3, and we also know these Q values, we can calculate, for example, for C1 and C2, we can calculate D plus 1, 2, and for C1 and C3, we can calculate D plus 1, 3. So of course, we can also calculate D plus 2, 3, which measures the discrepancy between pairs of communities. And they show that exact recovery is achievable if the minimal value of this Ch divergence between any two pairs of communities is greater than 1, then we can achieve exact recovery. And on the other hand, if this quantity is less than 1, then it is impossible to achieve exact recovery. So roughly speaking, these examples, we require that both D plus 1, 2, 1, 3, and 2, 3, all of the three quantities should be greater than 1 in order to achieve exact recovery. So this is the fundamental limits of exact recovery under the general SBM. Yeah, so up to now, I have completed the first part of the talk. So if you have any question, we can.
Eric, I had one question.
Yes.
So I've not come across Chernoff-Hellinger divergence before. So does it simplify to some other well-known divergence or distance metric? Or
yeah. So if you take t equals to half, then it goes to the Hellinger distance. Yeah, and it also it also has a form of F divergence. So yeah, but it can be regarded as a special case of F divergence.
Okay.
Yeah. Any other question?
Hey Eric, Qiaosheng here.
Oh, hi. Yeah.
So, so in the if the QIIs are all different, then so right now in your model you're only interested in partitioning it to subsets, and you don't really care about the labels corresponding to each subset, right? So for example, you don't care whether you classify those as blue or yellow or gray, right?
Yeah,
but
exactly.
if the QIIs are different, then you should also be able to do that, right?
Yeah. When there is a when there is a symmetry, then it is impossible to do
Correct.
that.
Yeah.
But yeah.
Sure. Yeah. But yeah, maybe also even the QIAs are the same, but the QIJs are
different. Yeah, it may still be able to do that. Yeah. So we introduced the permutation just to ensure that under the very symmetric case, we cannot distinguish the labels, the colors.
Okay. Another question is, I mean, so is it possible to do exact recovery for for the general SBM by repeatedly sort of doing it using algorithms for the two community SBM or something like that?
Yeah. First of all, the binary symmetric SVM contains only the equal size communities, and so I think there's some problem.
Right. Okay.
Yeah.
So for the general SBM, are there known like efficient algorithms?
Yes, efficient algorithms.
So similar to the ones like using SDPs or spectral.
Yeah, but actually, I don't think SDP. I'm not sure about SDP because people show that SDP is very effective in the symmetric case, but once the communities are the size of each community are quite different, just naively applying the standard SDP does not work. Maybe some people has studied SDP very extensively. Maybe it is possible to also solve this asymmetric case. But I think just in the previous several years, I think people just say that SDP is not suitable for solving the asymmetric case. But spectral method is quite effective in solving this asymmetric case.
I see. Okay. All right. Thanks. Yeah. So there's one more question in the chat box. So Harshan is asking, are there fundamental limits on multiple measurement models? So when there are two or more graphs which are observed from the same underlying probabilities?
Two graphs are generated according to the. There's no connection between the two graphs.
I'm not sure. So Harshan, maybe you can unmute yourself if you want to ask.
Oh yeah, I think I was thinking about the graph as just a single graph with some q value being 0. So then, for example, if let's say Q13 and Q23 equals to 0, then we will get this graph and this graph, which are two separated graphs.
Okay, but yeah, I'm not sure if this was the question, but perhaps I guess once you again, if this interpretation is right, then you first partition the graphs into communities, and conditioned on the communities, I guess you generate random graphs. So you generate the multiple copies of the graph. Basically, you generate the edges.
Yeah. Multiple copies of the graph. Yeah.
Yes. So I guess two random graphs conditioned on the same community structure.
Oh, I see. So you observe two graphs. So can this
help?
Can this information help you to better?
Yes.
Oh, I see. Yeah, I think so, right?
So it should be, but probably maybe do the fundamental limits change, or is it?
Yeah, since I think I believe it helps. So yeah, I think.
But has this been studied before?
I'm not sure. Yeah, but maybe the problem, I think, should not be very hard if you just have copies.
Okay.
Yeah, but I'm not sure whether
people have studied the version that if you sample multiple copies from the same underlying model, let's say Qiaosheng, they can learn the graph structure, for example. Let's say the model is Ising model or something, but this is the overkill because you know the structure, of course, you know the community. But I'm sure for this problem, if people have looked at the multiple measurement model.
Yeah, I don't know whether it has been studied, but it looks like that just having two copies just add more information for us to learn this underlying communities.
Sure.
Yeah, Qiaosheng, I'm sorry I was unable to unmute at that point in time. Thanks, Eric. Thanks. I think that's basically the question that was in mind. Essentially, this was motivated from a network point of view, wherein you, some sense, get this type of information or graphs through packets, and then when you have multiple packets coming in, whether it would be possible to achieve better sort of accuracy when we have multiple graphs coming from the same piece, same QIJs and QIIs.
Okay, thanks. Yeah.
Okay, thanks.
Thanks. Do we have one more questions? So otherwise we can continue to the second part. Okay, so let's continue. So in the second part of the talk, I will talk about community detection on hypergraphs. So as you all know, in graphs, each edge connects only two nodes, but in hypergraph, each hyperedge contains more than two nodes. For example, in this hyperedge E1 may contain three nodes, and E2 may contain two nodes, and E3 may contain four nodes. So in the real-world applications, there are many examples of hypergraph. For example, in the Facebook, we can use edge to capture the friendship relation between any two users, but it is more proper to use hyperedge to capture the chat group relationship, which consists of multiple users. And in particular, people are interested in some very special models, which is D-uniform hypergraph, in which case all the hyperedges contains exactly D nodes. And of course, if we set D equals to 2, then 2 uniform hypergraph is just a standard graph. So since the hypergraph is very common in the real-world applications, so people has also studied community detection on hypergraph for many years. And there is a very popular model, which is called the D-uniform hypergraph stochastic block model, which is the HSBM. And in particular, if we set D equals to 2, then 2 HSBM is just the standard SBM. So previously, there has been some work considering the HSBM, but most of the work from an algorithm perspective, and they also provide some theoretical guarantees. For example, there are some spectral clustering algorithm and also STB-based algorithm, and also tensor decomposition-based algorithm. And our focus is slightly different. We focus on the exact recovery criteria of the DHSBM. That is, we want to recover with probability approaching 1. We want to ensures the misclassification proportion between the ground truth and the estimate x hat equals to 0 exactly. And we have noticed that in 2018, some researchers have studied a simple version of this DHSBM, which is a binary symmetric DHSBM, in which case they have two equal-sized communities, and the hyperedge probabilities is either alpha or beta. So alpha means that if D nodes belongs to the same community, then they are connected with this D node will be generated as a hyperedge with probability alpha, and otherwise the D nodes will be generated as a hyperedge with probability beta. So we note that this work is a little bit restrictive. So in our work we consider the general DHSBM. So in our case, the number of communities is k, which may be greater or equals to 2, and we also do not impose the equal-sized constraints. And also the hyperedge probability depends on it's not only alpha and beta, but depends on the community membership of the D nodes, which we will introduce in the next slides. And also, as just I mentioned that for the binary symmetric DHSBM, they use a SDP-based method, but this method is usually hard to extend to the asymmetric case. So we use a spectral classing method plus the local refinement step. So this is the focus of our work. And in the next slides, I will introduce the model of general DHSBM. So this is actually quite similar to the standard SBM. So the N nodes are partitioned into k communities of size P1, P2, all the way to Pk. And for each set of D nodes, it is generated as a hyperedge with a certain probability. So I will introduce what's the meaning of the certain probabilities, so which requires some definitions. So we define the community membership of D nodes as a length k vector T comprising T1, T2, all the way to Tk, where Ti is the number of nodes that belong to community Ci. And also, in order to illustrate this definition, we use an example of 3HSBM, which contains 7 nodes and 3 communities, where these 2 nodes belongs to community 1, and this community 2, and this community 3. So if we consider a set of 3 nodes containing nodes 1, 5, 6, then the community membership is just 102 because node 1 belongs to community 1, and node 5 and 6 belongs to community 3. So the membership is 102. And similarly, for the set of nodes containing nodes 2, 6, 7, the community membership is also 102. And for this set 1, 3, 4, the community membership is 120. Sorry. So this basically was the meaning of the community membership of D nodes. And for any set of nodes with cardinality D, and if the community membership is T, then the probability of being a hyperedge is represented by Qt. So let's go back to this example. So for the first 2 set of nodes, since the community membership T equals to 102, then the hyperedge probability is given by this Q102. So although these 2 sets are different, but the probability that they are generated to a hyperedge is the same. And for this set 1, 3, 4, and the hyperedge probability is Q120, which is in general different from this Q102. So basically, this is the probability that any D nodes are generated to a hyperedge. And again, for the general DHSBM, we are still interested in the log degree regime, where this Qt, this probability Qt, scale as order log n divided by n to the power d minus 1. And in particular, we use this capital Qt to denote the pre-constant. And this is how we generate the random hypergraph under the general DHSBM. So far so good. Okay. So any questions?
Eric, I had just one question here. I'm not sure if this is, I mean, this is going back to the definition of the P vector. So here, when we have P1, P2, Pk, are these in the analysis when we characterize the threshold? Is it necessary that the Pi is the absolute constant? Like, could they, for example, depend on n, like, like the number? I don't even know if that's a painful question, so I just thought.
Yeah, that is a good question. So in our work, we require this P to be a constant. We do not consider the case that P scale as n.
Okay. Oh, you need that, right? Okay,
yeah, we need this condition. Yeah.
Okay.
So let's continue.
Eric, yeah. So I guess Professor Manjunath has a question.
Yeah. Can I ask a quick question? So what is the interpretation of a hyperedge here? I mean, I can understand that. I mean, I see that it matching the definition of an hyperedge in a hypergraph.
Yeah.
What is the interpretation? I mean, why would you want to draw hyperedge in that manner? Is it because of the way you collect information, or?
Yeah. Because intuitively, if the probability that one hyperedge generate depends on the community that the node belongs to, right?
No,
so,
I mean, no. So are you going to consider every combination of 3 nodes, 4 nodes, 5 nodes?
Yes.
You're going to.
Yes.
Yeah. Could you go ahead? Sorry.
Yeah. We only consider the hypergraph with a fixed number of nodes.
So you will consider you will look at every combination and see if you have an edge between them. Okay.
Yeah. Yes.
So the D is that what you call D?
Yes.
Yeah, okay. So D is sort of fixed in the model.
Yeah. Fixed.
D is fixed in the model. Okay.
Yeah. For example, in this 3 HSBM, so we consider every combination of every subset of 3 nodes.
Yeah. So
among these 7 nodes.
Yeah. I'll just repeat my first question. So what is the motivation for considering this? I mean, how do you motivate this in the physical problem? Why would you consider every combination of D nodes? Because that's the way information is available, or?
Basically, it is an extension of the standard SBM. Where in the standard SBM, we measure we consider every pair of nodes to be generated as a graph.
I can understand it as an extension, but just the physics. I mean, what is the interpretation if there is one? See, in the old model, there is an edge if there is an edge represents some kind of. I mean, if you want to look at it in blocks or something like that, it represents a link from one to the other.
Okay.
What does a hyperedge represent here? What is the physical interpretation to that?
Okay. So
I mean, not having a physical interpretation is also fine, but I'm just curious to know if there is one.
Yeah. So basically, the motivation can be, for example, if we consider this node as the users in the social network, then maybe we have many chat groups. So for simplicity, we assume that every chat group is of size 3. So every 3 people form a group. Okay. So in principle, if let's say this nodes 5, 6, 7, they belong to the same communities. So it is very likely that they form a chat group, right? So on the other hand, if these 3 nodes does not belong to the same communities, then the probability that they form a chat group is much smaller, right? Yeah. So roughly speaking, I think it models such scenarios.
Okay.
Yeah.
Okay. Thanks.
Okay. Thanks. Okay. So basically, this is a general DHSBM. This is a model, and next we will go to the technical part. So before presenting the main result for exact recovery, we need some more definitions. First we define the community membership of any d-1 nodes as a length k vector m, which comprise m1, m2 all the way to mk, where mi denotes number of nodes, belonging to community CI. And also we define the set of this set M as a set of possible M, roughly speaking, this M contains all possible community membership of D-1 nodes. As you can see that this set contains all length k vector whose element sums to D-1. So yeah, we need some more definitions. So if we have a node V belongs to a community CI, and we also have a set of D-1 nodes with community membership M, then we denote the joint community assignment, community membership of this this D nodes, because here is one node, here is D-1 nodes, as M plus I, where this vector contains k elements, and the ith elements equals to mi plus 1, and all the other elements is exactly the same as the elements in M. So so now let's give the last definition. So if node V belongs to a community CI, then one can calculate the expected number of hyperedges containing this node V, and also a set of D-1 nodes with community membership M. So this expected number is given by quantity because the first quantity Qm plus I is just the probability that these D nodes are generated as a hyperedge. So because this D-1 node has community membership M, and this one node belongs to CI, so the probability that this D nodes is generated as a hyperedge is given by this Qm plus I. And the second part is just the total number of combination of D-1 nodes which has a community assignment M. So if you just do some calculation, you can see that this quantity scale as order log n. So we want to define the normalized version by the mu m plus I, which is just this quantity normalized by log n. So here, this mu m plus I scale as a constant. So after defining this mu m plus I, we can define the so-called generalized Chernoff-Heidinger divergence we call Gch divergence between any two communities C and Cg as follows. So again, this is some this D plus Ij is some maximization over T, T from 0 to 1, and here we sum over all the community membership M belongs to the set M, and this quantity. So roughly speaking, this quantity is a function of mu m plus and mu m plus j. And so the interpretation of this quantity is that, so if we have a node belonging to Ci, then the expected number of hyperedges containing this node and a set of D-1 nodes with community membership M is represented by this mu m plus I. And but if this node belongs to Cg, then this expected number is represented by mu m plus j. So basically, we can use this mu plus I and mu plus j to denote the difference between the two communities, which is induced by a specific M. And then we sum over all possible M. And this gives us a very good measure of the discrepancy between two communities C and Cg. So this is Gch divergence between any two communities. So having defined the Gch divergence, we can state our result. So first, we state the converse result. One can show that exact recovery is impossible if the minimal Gch divergence between any pair of communities is less than 1. And on the other hand, this is a achievability result. We show that exact recovery is achievable if the minimal Gch divergence between any two pair of communities is greater than 1. And we have one more condition, is that the second order degree profile of each community is different. So I have not defined what is a second order degree profile, But roughly speaking, it is some properties that is associated with each communities. For example, for community CI, here is an expression of the second degree profile of CI, and basically it is a length K vector. And this condition says that if the K communities C1, C2, all the way to CK, they have different second order degree profile, then this condition is satisfied. And if the first condition also satisfies, then we can do the exact recovery. So we also design an efficient algorithm to achieve this for this achievability part. So as you can see, when the model satisfies condition 2, when this condition 2 is satisfied, then we have a sharp threshold. That is, exact recovery is achievable when this quantity is greater than 1, and impossible if this quantity is less than 1. But when this second condition does not hold, if the second order degree profile of of any two communities is the same, then our efficient algorithm does not achieve this, does not achieve exact recovery. So, but the converse result still holds. So there's an initial question, which is whether the minimal Gch divergence is greater than is sufficient for achieving exact recovery. So this is a problem that we want to answer in the future. And also, if we do some sanity check, if we set d equals to 2, where this 2 HSBM is nothing but the standard SBM, so we can check that this condition 1 automatically implies condition 2, which means that we in this standard SBM, we do not need to worry about the second condition. We can just ignore the second condition. And in this case, we notice that the achievability and the converse match. So we also recover the information theoretical result for exact recovery for a standard SBM, which has been developed by Abbe and Sandon. So this is the main result of our work. So we generalize the result by Abbe and Sandon for standard SBM, but we do not fully characterize the fundamental limits because of the existence of the second condition. So any question? So if no, I can go to the achievability part. I will describe our efficient algorithm. So I think even if you don't care about the fundamental limits, but the algorithm itself is still of some interest. So the outline of our algorithm.
Eric, this is Amitabh. I just had one question. So the regime where that the d value is exact, the min of d is exactly equal to 1, is that in general, is that meaningful, or is it it's kind of subsumed in one of these things? Yeah,
it's meaningful, but in our case, we do not consider the case, because I think if making d plus this quantity exactly equals to 1, it will need very careful analysis.
Okay, and is it done for the regular SBM? Like
for regular SBM, it I think they show that equals to 1 is also okay.
Oh, okay. Thank you.
Yeah, thanks. So now let's go to our algorithm. We use a two-stage algorithm, which follows from global to local principle. In the first stage, we use hypergraph spectral clustering based on observed hypergraph. And in stage 1, after stage 1, we will output an initial estimate x hat 0, comprising n elements. And we hope that after staging 1, our initial estimate can achieve almost exact recovery. That is, we hope that the misclassification proportion between x and x hat 0 tends to 0 as n tends to infinity. And in fact, we can show that as long as the second order degree profiles of different communities are different, then we can achieve this. by applying stage 1. And after stage 1, we can show that most nodes are estimated correctly. And stage 2, in stage 2, we do the local refinement based on the output of stage 1, this x hat 0, and also the observed hypergraph. So basically, we will refine the estimate of each node individually via a MAP estimator. And so as we do it for each node individually, and then finally we can obtain an final estimate x hat, which also comprising n elements. And we show, and the goal for the stage 2 is to show that the final estimate achieve exact recovery. That is the misclassification proportion between x and x hat equals to 0 exactly. And in fact, we can show that as long as this minimal Gch divergence is greater than 1, then we can achieve this threshold. We can achieve exact recovery. So after stage 2, all the nodes are estimated correctly. So basically, this is the outline of the algorithm. And next, I will go to the stage 1. So because we have observed a hypergraph, so we can construct a so-called binary incident matrix H according to the observed hypergraph. So this matrix H contains n rows corresponding to n nodes, and also n choose d columns corresponding to all possible hyperedges, which contains d nodes. So we can also fill this matrix. So basically, H VE equals to 1 if hypergraph E appears in the hypergraph and also E contains node V. So let's look at the figure. So suppose that this hypergraph E2 appears in the suppose this hyperedge E2 appears in the hypergraph, and it contains, and also this hyperedge E2 contains 3 nodes, V1, V2, and Vn. So we just write 1, 1, 1 here, and all the other elements are 0. And similarly, so if the last hyperedge appears in the hypergraph, and it also contains 3 nodes, let's say 2 minus 1, n, then we will write 1, 3 ones here, and all the other elements are 0. And for all the other hyperedges which does not appear in the hypergraph, then we just write 0. So this is the binary incident matrix. We just represent the hypergraph. So so next we will calculate the hypergraph Laplacian L, which is just H times H transpose, and then minus the diagonal matrix, where the elements is D1, D2 all the way to Dn, where dV is the degree of node V. So after this operation, we get a n by n matrix L, which we called hypergraph Laplacian. And you note that this L is an n by n symmetric matrix, and the diagonal element are zeros. And also for each element Lij, it represents the number of hyperedges containing both node I and node J. So it's the operational meaning of this hypergraph Laplacian L. So the next step is to trim the nodes that has significantly higher degrees. So to do so, we define a set gamma, which contains all the nodes whose degree is less than or equals to some large number tau. And then we zero out all the rows and columns corresponding to the which does not belong to this gamma. So for example, if the last node has much higher degree and does not belong to this gamma, then we will just make the last row and last column corresponding to this node all zeros. So we got the so-called trimmed hypergraph Laplacian. And the next step is to perform a singular value decomposition on this trimmed hypergraph Laplacian L gamma, and then we can obtain a rank K approximation L gamma K. So after obtaining this rank K approximation, we can then bound the Frobenius norm between this n matrix between this n matrix L gamma k and the expected of L gamma. So where the expectation is over the generation process of the hypergraph. So that is these two matrices are quite similar, are quite close to each other in the Frobenius norm. And now let's look at what is this expected L gamma, this E L gamma. So we notice that for nodes in the same communities, so if we imagine that there are 4 nodes which belongs to community C1, and for nodes belongs to the same communities, actually they have the same statistic properties. So if you just do the expectation, if you just calculate the expected value of this L gamma, it turns out that the nodes, for the nodes belonging to the same community C1, their corresponding 4 columns are exactly the same. So these 4 columns are identical. And similarly, if we have 3 more nodes which belongs to community C2, then one can show that the 3 corresponding columns are identical. And the same for the third communities, the 5 columns corresponding to the nodes in community C3 are identical. So if we map these columns into a 2-dimensional plane, then one can show that they are quite separated. And you can calculate the distance between any pair of the 2 nodes. And basically, this is a property of this EL gamma. And next, because we know that this L gamma k is very close to EL gamma in Frobenius norm, so one can also express this Frobenius norm as for each column, I calculate the distance between the columns in EL gamma and the columns in L gamma k, and you can just represent the Frobenius norm of 2 matrices as such L2 distance between the columns, and then you sum over all the columns, and it turns out that this quantity is also very small, which means that the columns of L gamma k is actually quite close to EL gamma. So we use we leverage some techniques in random matrix theory to show that these 2 matrices are very similar, and also the columns of the 2 matrices are also very similar. So if we look at the 4 columns corresponding to community C1, then we can see that although they may not be exactly the same, but they actually are quite close to the expectation denoted here. Yeah, because this L gamma k is a realization, and this EL gamma is an expectation. So of course, for each columns in this L gamma k, they are not identical, but they are quite close to the expectation. And similarly for C2 and C3, the columns are also quite close to the expectation. So if we map all the columns into a 2D plane, we can see that, okay, the 4 nodes corresponding to the 4 columns are quite close, and also the 3 nodes corresponding to the 3 columns are quite close, and so on and so forth. And of course, there may be some outliers, but it does not matter. So because in stage 1, our objective is just to estimate most of the node correctly instead of estimate all the node correctly. So since columns are so well separated, and the nodes in each column is very close to each other, then we can use some standard clustering method to just do some clustering. And our goal is to make sure that most nodes are estimated correctly after stage 1, and we don't need to care about this outlier. So basically, this is stage 1, and why using this approach works. And after stage 1, after making sure that most of the nodes are estimated correctly, then we go to stage 2, because stage 2, in stage 2, we perform local refinement steps for each node individually, and stage 2 relies critically on both the observed hypergraph and the initial estimate x hat 1 obtained in stage 1, x hat 0 obtained in stage 1. So specifically in stage 2, for each node V, we perform a MAP estimation. So here, the estimator X hat V equals to the argmax of I belongs to K, and we calculate the probability that XV equals to I given the observed hypergraph G and the initial estimate obtained in stage 1. But here the initial estimate is the initial estimate of all the node except this the node V itself. So for each node V, we calculate a MAP estimation, and we note that such MAP estimation is equivalent to a hypothesis test with independent but non-identically distributed samples. So one can then express the error probability of the MAP estimator, this probability that X hat V does not equal to XV in terms of variant of Chernoff information. And it turns out that this probability is approximately equals to n to the power minus the minimal Gch divergence between any two pairs, and plus some lower order term. And now it becomes clear that why we need this minimal Gch divergence. Minimal Gch divergence is greater than 1, because in this case, when this condition is satisfied, we can take a union bound over n nodes to ensure that the probability that there exists a V such that the MAP estimator does not make a mistake. This probability is very small, tends to 0 as n tends to infinity. So which means that with high probability, all the nodes can be estimated correctly. So this is our stage 2, and here there is a highlight idea why we need this term to be greater than 1 in order to make sure that all the nodes are estimated correctly. So next I will give some discussions. First, there is a subtle issue that I have not mentioned in previous slides. That is, actually, these two stages are not independent. So because in stage 1, we obtain an initial estimate X hat 0, but stage 2, we relies on, applying stage 2 relies on the initial estimate X hat 0. And we know that conditional on this X hat 0, the distribution of the hypergraph actually has been changed. So we need to be a little bit careful because this some independence issue may make the analysis incorrect. So our solution is to use a very use a kind of standard technique, which is so-called graph splitting or hypergraph splitting techniques. So in this, because the hypergraph is quite hard to illustrate, so here I just use a standard graph to illustrate this technique, graph splitting. So first, we have n nodes corresponding to the n users or in the Facebook, and first we can draw a complete graph on these n nodes, and then we want to partition this complete graph into two parts. The first part is, in the first part, we just randomly sample some edges in the complete graph to form the first graph. And for the second graph, the edge set is just the complement of the edge set in the first graph. So roughly speaking, we want to ensure that the first graph is sparse, which contains only a vanishing fraction of edges in this complete graph. And the second graph is very dense, which contains almost all the edges in the complete graph. And then we can show that for stage 1, it suffices to use this very sparse graph. So even if we use a very sparse graph, we can still obtain a very good initial estimate. And for stage 2, we use the dense graph, which is almost the same as the original complete graph, and we show that running stage 2 on this dense graph will be will be good enough to ensure exact recovery. So basically, this is some subtle problem that we need to take care in the analysis and in the proof. And so this kind of technique is a little bit complicated. But it just helped me to make the analysis correct. And actually, when we do some experiments, I don't think we need this graph splitting technique. And maybe we can just when we do some experiment, we can just run stage 1, stage 2 on the same graph, so to make the implementation easier. So this is just a subtle problem arise in the proof. And also, I want to we can also improve our algorithm because in the current version of our paper, we assume that we know the model's parameters. For example, the number of communities, the relative size P, and the hyperedge probability Q are both known to the estimator. But actually, if we do some slightly fancy technique, we can also estimate these model parameters on the fly. So we do not know the model parameters a priori, and we can also estimate this correctly. And the last part is that, as you know, in our result, we have a very annoying second-order degree profile condition. So in future work, of course we want to get rid of this condition so that we can establish a sharp threshold for exact recovery. So so why we have this second-order degree profile condition is that we apply the clustering algorithm on the hypergraph Laplacian L, where this L is just an n by n matrix, and actually we just do some processing on the hypergraph H, and we multiply H by this H transpose. So where H is actually a very high-dimensional matrix, and then we map this H to a low-dimensional matrix L. So in the process of calculating this L, we actually lose some information for distinguish the communities with the same second-order degree profile. So I believe this is the reason why we have this annoying condition. So in future work, it may be promising to apply the clustering algorithm on the adjacency tensor directly, or maybe on this H matrix directly, without mapping this H to the low-dimensional matrix L. So maybe by using this such scheme, such algorithm, we can get rid of this condition. And we can also establish the fundamental limits of exact recovery in the HSBM. So this is our algorithm part. So any question? So please feel free to ask. So if no, I will go to the converse part. So okay, so let's continue, and I will go to the converse part. So the high-level idea of the converse part is as follows. So because the hypergraph is a little bit hard to illustrate, so here we just use a very simple HSBM to illustrate the high-level idea of our converse result. And of course, this high-level idea is inspired by Abbe and Sandon in their original paper. So here we have two communities, C1 and C2. And first, we randomly select a subset of nodes S, and the size is of cardinality. The size is n divided by log n to the power 3, which is the size of S is much smaller compared to the whole graph. And one can show that if the minimal Gch divergence between any two pair of communities is less than 1, then there will exist a node V1 which belongs to the intersection between C1 and S, and there is also a node V2 which belongs to the intersection of C2 and S. So we have these two nodes, and these two nodes satisfy the following conditions. The first condition is that, sorry, not condition, satisfies, has the following properties. So this property is that, seeing that the edge between E1 and the nodes in C1 exclude this S is equals to the number of edges between V2 and the number and the nodes in C1 exclude S. So that means both V1 and V2 have the same connection to this subset. And the second property is that for V1 and V2, they have the same connection to the set C2 exclude S, meaning that these two nodes have the same connection to this subset. And also, the third property is that this V1 and V2 do not connect to any other node in S. So, which means this V1 does not connect to these nodes in the subset S, and the same is true for V2. So, based on these properties, one can conclude that this V1 and V2 are indistinguishable because, of course, a priori we don't know the colors of each community, each nodes. We don't know the communities, and we can show that even if there is an oracle who tells us the colors of all the nodes except V1 and V2, then we still any algorithm are still unable to distinguish V1 and V2 because, as you can see, this V1 and V2 has the same connection to this subset and have the same connection to this subset. So there's no way that one can distinguish V1 and V2. So that is basically the reason why exact recovery is impossible. So basically, one can show that as long as this condition, this minimal Gch divergence is less than 1, then we will have such pair of nodes V1 and V2, which are indistinguishable, and then exact recovery is impossible. So of course, this is this graph is illustrated for the SBM, but actually for a more complicated HSBM, one can still use similar ideas to show such converse result. So this is okay. This is all of my talk. So thanks for your attention. Please feel free to ask any question or give any comments.
Thanks, Eric. That was a really interesting talk. Yeah, maybe one quick question before I open the floor to questions.
Yeah.
So in the achievability part, so essentially, you can use any hypergraph partitioning algorithm for stage 1, right?
Yes, basically we apply some we apply some very simple clustering algorithm on the columns of this matrix, our gamma k.
Correct. So and I guess the requirement on the second order degree profile comes because of that. As you mentioned, it comes because of the spectral clustering algorithm that you're using.
Yes.
Right. But are there other known other kind of clustering algorithms which you can use, which somehow allows you to avoid this?
Yeah. I think there. Some people from Statistics Society, they also studied some hypergraph clustering algorithm based on the tensors instead of the matrix. Yeah, so I think, I have noticed that one paper is focusing on the tensor decomposition based algorithm. Yeah, but the analysis is quite complicated. So, and also our model is quite complicated. So it is also kind of challenging to apply their idea or modify their algorithm to fit to our problem.
Okay. I mean, because again, I am not sure about probably there are a lot of other intricate details involved, but can't you just use maybe a different clustering algorithm as a black box and then conditioned on that? So So I guess all you need is that the stage 1 gives you a certain recovery.
Yeah, exactly.
And then you can independently apply stage 2.
Yes.
Right.
Yes. Yes.
So depending on what are the requirements for stage 1 to function well, everything else goes through.
Yes. Yes. Exactly. We want to design some algorithm for stage 1 just to ensure most nodes are estimated correctly.
Sure.
Yes. So stage 2 is actually it's kind of standard.
Okay. But also I guess so I guess you're also aiming for an efficient algorithm, right?
Yes. Yes.
But suppose you didn't care about that and you didn't care about the complexity.
Yeah.
Could you still get a better some better thresholds, or is it too hard to analyze?
Yeah, actually, I think it's very very hard because we can directly use MAP, the MAP algorithm, MAP estimator. Yeah, but actually the analysis, a little bit hard. Yeah. Yeah, because for our algorithms, the good thing is that once we after stage 1 we obtain the good initial estimate, then the performing local MAP estimator for each node individually will be more tractable.
Yeah.
But I'm not sure. Yeah. Okay. Yeah, of course you can you can try MAT, but it becomes complicated.
Okay. So maybe one last question. So have people studied hypergraph SBMs with almost exact recovery?
Yes, I think this I have mentioned some algorithms, and so I think these guys also develop some algorithm, and they provide some theoretical guarantees, and they show that they can achieve almost exact recovery under some regime. But the problem is that the model that they considered is not as general as our model. So, for example, for this binary symmetric DHSBM, so of course it is quite restrictive. Yeah, but for the other models that they studied, they are still not as general as our model. So it is hard to, roughly speaking, these algorithms are not readily available for our objective. So
Okay, thanks. Yeah, so Prasad has a question. Prasad.
Hi, Eric. Am I audible?
Yeah.
Yeah. So the question which I had is regarding the robustness of your scheme algorithm,
yes,
achievability algorithm with respect to the problem parameters, particularly the probabilities and so on.
Yes.
So do you have some analysis or guarantees on that? Suppose you did not, so there are some errors in the estimates. Does it somehow reflect in the threshold or something like that, for example?
Oh, you mean that in the case that we don't know for example, the p vector. Correct. And the first of all, in our work, we at the current stage we still require the knowledge. So talking about maybe the future, so whether we can design an algorithm to which does not require the knowledge of this P and Q, right? So I think once we do the SVD, for example, in stage 1, if we do the SVD singular value decomposition, of course we need the knowledge of K. But I think there are some other algorithms which can even estimate the value of the singular value, and then because for this algorithm, actually only the first K singular value will be significantly larger than the K+1 singular value, So if we can if we can make use of these properties, then it may not be necessary to know the value of k a priori. So once we overcome these difficulties, we can follow these ideas just to estimate all the nodes, estimate most of the nodes. That is, we get a good initial partition, and then we can, once we get a good initial partition, then we can estimate the p vector, right? This p1, p2, p3. We just divided the number of nodes in these communities divided by n. So we know the p vectors, and we can also estimate the connection probabilities between any two the connection probability between any two communities, right? Yeah, so I think it is plausible to design algorithm without the knowledge of these model parameters.
Thanks. So even if you had, so actually my intention was, let's say that you had an estimate, but the estimate was off from the correct values by some epsilon or something, right? By at most epsilon. So I was just thinking whether it would somehow manifest in instead of having a sharp threshold. You had a more weaker threshold for which you are able to do the detection as long as this divergence is greater than that, but it's not a sharp threshold, right?
In the case that you mentioned, so when we you said when the maybe the p-value and the q are perturbed, right? Not the exact value.
Exactly. Yes.
Yeah. So then I think the second stage will be affected. Yeah, because it's because the second stage relies critically on the MAP estimator, where this probability is over the generation of the hypergraph. So if the probability measure has been changed, then I don't know how much it will be changed. So only plus or minus some epsilon, very small quantity.
Right.
Yeah, I think if it is small enough, it can be. It should be okay to tolerate such perturbation. But I think when it's large by some constantly large quantity, then this will affect the threshold for exact recovery.
Right. And do you think the converse would still be reasonably, easy extension of what you have, or would that be far more complicated?
You mean for the for the model that you mentioned?
Yeah.
Converse. I don't have some ideas about this.
Sure. Thank you.
Yeah. Yes, thanks. So any other?
Yeah, is there any other question? Anybody? Okay. If not, then we should thank Eric. So thanks. You've been very patient with all our questions, and it's been a fantastic talk. So thank you very much. And yes, thank you again, everyone, for joining us today. And please look out to have a new talk coming up in the next one.
Okay, thank you everyone.
Thanks, Eric. It was a nice talk.
Thanks, Eric. It was a great talk.
Yeah, thanks. Yeah, sorry, I thought you were not able to get it.